Hey data junkies, welcome back to two-sample hypothesis testing on Z and T tests with your host, Shawn Janzen. I apologize if my voice is going out a little bit. I'm fighting about a hoarseness, but we got to keep pushing through. So at this point, we're at topic 9.6 on proportions, and we're going to be looking at the two-sample t-tests for proportions specifically in this video. Future videos are going to be looking at effect sizes and power testing for the two-sample tests. Now, when we talk about two-sample proportions testing, the first thing we have to keep under our belts is that we're getting Z statistics, not T. And we're going to be using alpha as a way to obtain our critical values, just like we would with any other Z test. Now, the sampling for these particular ones requires that we have random sampling and that the samples are independent. This, again, is the general baseline assumption for proportion testing in general and the vast majority of the statistical tests that we're doing here. We also say that the samples should include at least 10 successes and 10 failures. This is a carryover from the one sample version, and that the population is at least 20 times as big as its sample. I threw this one in here not because it's as strict of a requirement, but it's similar to another one that you've seen previously where it says your sample should be less than 10% of the population. And so this is an equivalent assumption to it. If you have it that your sample is less than 10% of the population, you're good. If your population is at least 20 times as big as the sample, you're good. These are just two different ways of sort of getting at the same idea, and I introduced this one just because I know some of you go look things up on the internet, and you're going to see different assumption statements. I just want to put it out here so you're hearing both sides of the story. But they get to the same thing. Now with two-sample proportions testing, just a quick recap on the symbols that we're going to be using in here for our terminology. So the letter P is our population parameter, and P with a little hat on it, we call it P hat, or P sub S, and that is talking about the estimate of the population's parameter. So the estimate is talking about from our samples. It's not the population parameter itself. It's our best guess as we're getting close towards it. The hypothesis statements for when we do these, the not, H naught, is going to be looking at P sub 1 is equal to P sub 2, and these P sub 1s and 2s, these are referring to the group numbers because now we're doing two different samples. Just like when we did independent sample t-tests and we had group 1, group 2 with X bars, now we have them with P's for proportions. So the proportion of group 1 is equal to the proportion of group 2. Whereas in the alternative, we're simply stating that they are not equal, that the proportion of group 1 is not equal to the proportion of group 2. It is entirely plausible if you wanted to do a directional test, a one-tailed test, you could certainly do that, in which case you would then indicate if you believe the proportion of group 1 is larger than group 2, or the other way around if the proportion of group 1 is smaller than group 2. We also have to keep in mind that we are sufficiently large. This ties back to the assumption before about the 10 successes and 10 failures. So here I just have a brief recap for you on how we define those successes and failures. And because we have two groups, we need this to apply to both groups. So with group 1, you need to take sample size times P hat and see if that's larger than 10, as well as sample size times 1 minus P hat, if that's larger than 10. Repeat for group 2. If you meet these, then we can go ahead and move on. And here is the formula for the two-sample proportions testing. Note it's very similar to what we had before with the one sample, except instead of having the population proportion being subtracted from the sample proportion, we have proportion of group 1 minus proportion of group 2 in the numerator. In the denominator, where we have the standard error of the difference, this again looks similar to how it was with the one sample, except underneath that square root sign, we have a separate one for each group. And we have this thing called P hat sub C, and this is where it gets a little bit different. So P hat sub C is a method in which we are combining the sample sizes and proportional data into a particular statistic called P hat sub C that we then insert into the denominator to help us calculate the standard error of the difference for the proportions. It's an extra step, but one that we just have to go through. And I'm going to use this formula here to answer a question exampled. Is there a proportional difference between men and women and their belief that we, the U.S., spend too much on the space exploration program, and we're going to use an alpha at 0.05. Now when I want to go ahead and look at this and answer if there's a proportional difference between men and women and their belief that we, the U.S., spend too little on space exploration, I'm using the General Social Survey 2016 data, and I've made a bivariate table here with our two variables of interest, sex, which indicates as men and women, and NatSpec, which indicates if we are spending too little, about right, or too much on our space exploration programs. I have this set for a column sorting, column addition. That way we can see what percentage of all men believe that we spend too little compared to what percentage of all women believe we spend too little, and we can compare across. And what we can see is that there are about 139 men, and 28% of all men believe that we spend too little. And of the women that say we spend too little, there's 142, and that's 18%. Note the frequencies are relatively similar to each other overall, but the percentages are about 10% off. So don't let the frequencies fool you. The frequencies are relative to the sum of men and the sum of women that help us generate those percentages, which is why we look at the percentages in the first place. So is there a difference between the 28% men and the 18% women? Let's go ahead and plug this into the two sample proportions testing, and I'm going to start off by generating p hat sub c. And p hat sub c, I go ahead and I use both the frequencies and the proportions up in the numerator there for group 1 and group 2, and then in the denominator I'm summing together the two group sizes, the two frequencies. And when I work the math across, I come up with a p hat sub c of 0.23. I take that 0.23 and I reinsert that into the denominator area where I'm calculating the standard error of the difference. I'm also going to plug back in the N1 and N2 sample sizes of the groups. I'm also going to, up in the numerator, put in that 0.28 and 0.18 for the two proportions for men and women, and I'm going to work the math through, and I'm going to come up with a z-score of 1.993. 1993. So then we have to figure out, where do we go from here? Well, I just did this by hand, and if I want, I'm going to go ahead and make R do it for me, just as a calculator version to kind of confirm that I have my answers right. So on the screen, I'm showing you just how I can quickly code each of the numerical values into an object, P1, P2, N1, N2, respectively. I use those, I recreate the formula that makes P hat sub C, and I just identify it into an object I call PC. Then I can go ahead and round PC to see that I can confirm that it was the 0.23, and then I've gone ahead and recreated the formula for the denominator, which is the standard error of the difference, using P hat sub C, N1 and N2. Then I go ahead and create that SE object, which I then plug into another formula for the z-score with P1 minus P2 divided by standard error. And that generates my z, which R tells me is 1.993165, and we are right on target. Of course, if you want to go ahead and let R recreate formulas with you, you could put these all into one giant long formula. I just found it easier to break up to kind of help pieces moving along in case I had to do any troubleshooting, and it's easier to explain. So let's go ahead and reflect on this while we're looking up our critical value. We asked, is there a proportional difference between men and women and the belief that we, the U.S., spend too little on the space exploration program? And when I asked if there was a difference, I wasn't looking in any particular direction. This was a non-directional term, so this is going to be a two-tailed test. And given that we're using an alpha of 0.05, then I know that I can look this up on a z-table or use the qnorm function in R to figure out that my z-critical value is going to be plus and minus 1.96. And so we're going to compare if 1.99 is larger than 1.96. And indeed it is, so we can say it's statistically significant. Now I'm going to enter in a little sprinkle of skepticism here, because it's statistically significant when we're looking at the second decimal place, which if you've looked at a lot of these statistical tables like the z-table, that number changes quite a bit. So we are statistically significant, but just barely. Okay, we're just barely statistically significant. Any alteration in alpha, and it could take us one way or the other, or any alteration in our data if we were to go out and get another sample, we're going to be more likely to either be one way or the other, because this is pretty on the line. But if I want to go ahead and also ask ourselves so we can check this out, I'm going to give you a few questions that we can work on this with. And I want you to go ahead and pause the video in between each of these questions to see if you can figure it out. So the first one we're going to ask is, if it was a one-tail test with more men than women, would it still be statistically significant? So go ahead and pause the video and think about this for a minute. I'll wait. Okay, so the z-score we obtained is not going to change. It's 1.99. That's going to be the same regardless. What's going to change is how we calculate z. And so when we're dealing with the one-tail test, more men than women, we're specifying more men. So we have to make sure that men are coded as P1 when we do the P1 minus P2. And a null is going to take on that directional approach to say that P1 is greater than P2. So it's going to be greater than 0. And when we're doing the one-tail test at alpha 0.05, we come up with a z-score of 1.65. Recall that men were 28% and women were 18%. So we have a positive difference of 28% minus 18% is plus 10%. And that number then is going to mean that we have a positive 1.99 z-score, and it's going to be larger than the 1.65, so we're still going to be statistically significant. This makes sense because the one-tail version is going to have that lower barrier to entry to get into the critical region than the two-tail, and we were fine at the two-tail. So let's go ahead and flip the question to our second area here, where we're asking, is the one-tail with more women than men going to be statistically significant? So take a moment, pause the video and think about this, and come back when you're ready. Okay, so this is a flip of what we just did, where we're wondering, it's still directional, but is it going to be statistically significant with more women than men? So in this case, we're making P1 women, because it's P1 minus P2. And in this case, we have 18% minus 28%, which is going to give us a negative 10%, which in that case is going to create a negative z-score obtained. So it's going to be negative 1.99. The slide up top is going to say positive 1.99. That was just a reference for where we started at. But in this case, it's going to generate a negative z of 1.99. And our z-score is still going to be on the positive for the critical of plus 1.65. So our z-score is going to be in the wrong side of the tail. And therefore, it's not going to be statistically significant in this case. Which, again, lines up if we're making sense, that there is a difference between men and women, but it is men that are that believe we are spending too little, more so than women. So let's ask about the third question. Would this still be statistically significant if alpha was 0.10? So we're talking about a two-tail 0.10. Go ahead and pause the video for a moment and come back when you're ready. Okay, so now that you're back, what we have is a z-critical of 1.65 plus or minus. Why is it 1.65? Because I was saying that this case is a two-tail alpha 0.10, so we split alpha in half at 0.05 on each side, and if you look up the z-scores at probably 0.05 and 0.95, we come up with plus and minus 1.65. And the z-score of 1.99 that we obtained is larger than our 1.65, regardless of which side of the tail we would be looking at. So yes, we are statistically significant, which again would make sense that we're significant at alpha 10 because we're also significant at alpha 0.05. So what about the last question we had here? Would it still be statistically significant if alpha was 0.01? Go ahead and pause the video for a moment and think about this and come back when you're ready. Okay, so we just got done saying that we were statistically significant when alpha was 0.05, but just barely. And when alpha was 0.10, we were definitely statistically significant because we were fine at 0.05. Now, we should be able to guess just by the patterns we're seeing here that when we make alpha smaller than where we were at 0.05, we're probably not going to be statistically significant because we were just on the cusp at 0.05. But let's go ahead and prove this mathematically. So when alpha is 0.01 and it's two-tailed, because I didn't mention any directionality, then we're going to have a z-critical value of plus or minus 2.58. And our z obtained of 1.99 is not larger than 2.58, so we're not going to be statistically significant, sorry to say. And that's going to go ahead and wrap up our examples and discussions on the two-sample proportions testing for the z-tests. And I'll see you in the next set of videos where we start to talk about effect size.